All right, so we've seen the formula now for average power. Let's just write it here again. P average being equal to the IRMS times the VRMS times the cosine of the phase shift between the voltage and the current. Okay, so we've seen this now a couple of different times, and I mentioned that this term right here, let me actually just use a different color. This term right here is called the apparent power. And so we can see that here, S. Right, that's this guy. S is the apparent power in my system. And so what does that even mean? So basically, if I have a system or a circuit that has an AC source, and again, I'm powering some kind of a load that's not purely resistive, this load is going to have some impedance that's going to have a real part and a reactive part, okay? And so this reactive part, of course, it could be some combination of capacitances and inductances in my circuit. And capacitances and inductances, like we said, they contribute to a phase shift between my voltage and my current, right? So I could have my source that looks like this, my source voltage, right? That would be this voltage here. And then I'm going to have some current flowing into my circuit, IS of t, driving this load. And because of the phase shift, or because of the reactance, this capacitances and inductance that I have in my load, my voltage and my current will not be in phase. So I might get something that looks more like this, right, for my current. And so we need to account for this phase shift here, which we talked about. There's going to be a phase shift phi between my voltage and my current, and that is going to be how I calculate my power factor, which is this term here, power factor. And that this phase shift is this phase shift, right? It's the difference in phase between my voltage signal and my current signal. So we talked about all of this. So what is the apparent power then? What is it really telling us? It's basically telling us what the power would be if my voltage and my current were in phase, right? It's basically saying let the cosine term go to 1, and we'll just look at the RMS voltage and the current like we did in the resistive case. And that's basically saying if my voltage and my current were in phase, what would the power be? That's the apparent power. And so the reason why it's called the apparent power is because it's apparent, or maybe it might be apparent to someone, that the power should still be calculated as the product of the voltage and current, even in the presence of this phase shift. But that's not the case. Maybe this is a bad name. I don't know how you feel about it. But that's why it's called apparent power. It is still the product of the voltage and the current, basically just leaving out the cosine term that we have here when we calculate real power or average power. Okay, again, this is also called real power, not necessarily called average power in all cases. And so that's all you really need to know about average power, other than that, in order to distinguish it from real power, they don't use units of watts. Instead, it's the same units. It's still current times voltage, but they actually use volt amperes, and they don't denote this in watts. It will always be denoted in volt amperes. So if you ever see something in units of volt amperes, then you know that we're talking about the apparent power and not the real power, okay? And so you may still be confused. What is the difference between apparent power and real power? We haven't talked about the power triangle just yet. I'm going to get there. But basically, there are several components of the power when we do AC power analysis and when we have a load that is not purely resistive, right? Like this load here has some resistance and it also has some reactance. And so the total load impedance is characterized by the resistance and by the reactance. And so there's a portion of the power that is supplied by the load, or that's produced by the source, that gets supplied to the load and that actually gets used by the load. It actually gets dissipated as energy in one way or another. There's also a portion of the power that does not get used by the load. Rather, it gets either sent back to the source or it gets stuck in the inductors and the capacitors in our circuit, which can store energy, right? And so people like to use this analogy. It's an okay analogy. I think it's worth showing. So let me move this actually out of the way, and I'll put it over here. Just put that like that, and let me paste this image in here. So they use this beer analogy. A lot of people like it. It's an okay analogy. And so it's basically showing you that in volt amperes, which is that's the unit that we use for apparent power. This is here on this beer analogy, volt amperes. They have it in kilovolt amperes because normally power systems are very large, like powering the grid or your city. So we're not usually going to be working with milliamps or milliwatts. We're going to be talking about kilovolts and kiloamps and huge currents and huge voltages, right? And so the analogy here is that the total amount of power supplied, right, by your source, the voltage times the current, it gives this amount of apparent power. This is the apparent amount of power that we could use if our load were just purely resistive, right? If we didn't have this reactance and we just had resistance here, my voltage and my current would be in phase, and this is the amount of power that we would have available to us, is this the total volume of beer in the glass. But because some of that energy gets stuck or wasted in the inductances and capacitances in my circuit, some of it is not usable, right? That's what's called reactive power, and we're going to talk about that in a few slides. But that is a portion of the apparent power, and the portion left over to us to actually use is the real power. That's this average power. That's the apparent power, right? The whole thing, but scaled down because of the phase shift, right? So we lose a little bit of this power that we had available to us due to that phase shift between the voltage and the current, which is, due to the reactance in our load or in our circuit, okay? And so I don't know how you feel about this analogy. I think it's pretty good at kind of getting the gist that there's a total volume of beer in this glass, but only this amount is actually beer that you're gonna drink and enjoy. Maybe you enjoy the foam too. Most people don't, but nonetheless, the idea here is to show you that there is some total amount of power here, the apparent power, that we could use if our reactance were just zero, but our reactance is often not zero in practical applications. There are inductances and capacitances which cause this phase shift, this very real phase shift, which results in some of our power not being used by the load, rather being stuck in our circuit or being sent back into our source when we want it all going to the load, right? And so in the case where the resistor is our entire impedance and we have no reactance, then the beer would fill the whole glass and we wouldn't have any foam here. Our reactive power would be zero and our apparent power would be equal to our real power. And that's exactly what we had in the resistive case, right? When we said that the average power is IRMS times VRMS, and we didn't even have the cosine term there because we just knew that it was the cosine of zero because the phase shift was zero, and this term goes to 1, and we just get left with this P average equals IRMS VRMS. And so that is the case where the real power here is equal to the apparent power, okay? Final takeaway from this slide, just remember that apparent power is measured in volt amperes, not in watts, although they are the same unit. It is used to distinguish the apparent power from the real power, which is measured in watts. Okay, so I'm going to go ahead and end this video. Hopefully that makes sense. And in the next video, we're going to do an example problem where we do some computations with a reactive load, okay? Something that's not purely resistive like this. Something that is like this is not purely resistive, okay? That would be a better way to say it. So I'm going to end this video right here.